Hello, and welcome to the third webinar in our series, Lunch, Learn, and Dance, Uses of Radiation. In this session, we will overview the types of radiation and their uses. My name is Lynn McDonald, and I will be the presenter for this portion of the webinar. I will be joined by Angelo de Torres at 12:30 Eastern, and he will lead us in dance. Also joining me are Maria Costa and Natalia Mosiani. They will help monitor the chat. Let's take a moment to go over the functionality of the Zoom webinar. The audio and video will be from the presenters only. We have found that although you can access the audio through the computer or telephone, the quality of sound tends to be better when listening from a computer. There is a chat feature where people can discuss. If you would like, take a moment now and say hello and where you are from. If you have questions arriving from the content, please enter them under the Q&A section. As the webinar is only a half hour in length and is immediately followed by our dance session, time may not permit me to answer them during the webinar. The answers will be posted on our website, along with a link to the video recording and a copy of the slides. This can be found under Education Webinars. I will be sending a confirmation of attendance email after the webinar and will include a link to the page with that communication. I will also include the topics covered and the length of time spent in the webinar, as some people have requested this to send to their professional association. Lastly, I have automatic closed captioning enabled in the slide presentation. If they are being blocked by your Zoom controls, you should be able to select a different way to view the webinar in Zoom, which will make them easier to see. In this webinar, you will learn about uses of radiation. We will start off with an overview of matter and energy, broad categories of radiation, and the difference between ionizing versus non-ionizing radiation. We will then look at radiation organized by the categories of nuclear particle radiation, particle accelerators, electromagnetic, waves and matter, and mixed field radiation. Next, we will look at uses for each type and how their properties will make them useful to their purpose. We will then look at applications which could use different sources to do a similar task. Please note that while this is a broad overview, it does not include every possible use or instance of where you may encounter radiation. Also, the focus of this webinar is the uses of radiation. For more details on radiation and its health effects, please see the past webinar, Understanding Radiation, and the upcoming webinar, Health Effects of Radiation. Physicists study the interaction of matter and energy. Matter is made of small particles called atoms. All matter has mass and takes up space. Energy is the ability to create change in matter. It has many different forms, but we often talk about two types of energy: kinetic, or the energy an object has due to its movement, and potential, which is stored energy. When energy is transferred out in straight lines, we call it radiation, and can take the form of beams, of particles, or waves. For the purposes of this webinar, we are going to group radiation into broad categories. Energy can be radiated away from a source, either through the movement of particles or waves. You can find radiation in the forms of streams of particles emanating from the nuclei of unstable radioactive atoms or from equipment designed for this purpose. Electromagnetic radiation is made of non-material particles called photons. You can also have energy travel through vibrations of material called a medium. Finally, there are some forms of radiation which are comprised of more than one type. No matter the type, radiation must interact with matter in order to deposit its energy into it. No matter what the source, radiation can be categorized as ionizing or non-ionizing. Ionizing radiation has enough energy to remove electrons from atoms. When this happens, it could cause the bonds that hold molecules together to break apart. On a larger scale, if this type of radiation hits living material, it could kill cells or cause damage to their DNA. These types of radiation tend to be federally regulated. Non-ionizing radiation does not have enough energy to remove electrons from atoms. Any damage that it does occurs mainly due to heating up the substance it interacts with or photochemical effects. These forms of radiation tend to be provincially regulated. The atom is made up of three types of particles: the proton, which is positively charged, the neutron, which is neutral, and the electron, which is negatively charged. Protons and neutrons bond together to form the nucleus of the atom, and electrons orbits around it. Most elements have a stable nucleus that does not easily break apart. Some elements have unstable versions which will naturally break apart to become more stable. Radiation that comes from the nucleus during the breakdown can take the forms of particles of matter, alpha, beta, or neutron radiation, or particles of pure energy called photons, gamma radiation. Alpha, beta, neutron, and gamma radiation are all ionizing. We will first talk about the types formed of matter and talk about gamma in the section about electromagnetic radiation. Alpha particles are made up of 2 protons and 2 neutrons ejected from the nucleus. They are a form of ionizing radiation. They have a charge of +2. Due to their relatively heavy mass and strong charge, they interact strongly with matter, so they deposit their energy very quickly. This also means that they do not penetrate deeply into material, roughly 7 centimeters in air. They cannot make it through a sheet of paper or the dead layer of our skin. Alpha is a concern, therefore, if it's being emitted inside a person. Alpha radiation is emitted from large unstable atoms. Elements like uranium and radon, which exist naturally in soil, emit alpha radiation from their nuclei. Beta radiation is an electron or positron, a type of antimatter, ejected from the nucleus of an atom which is trying to become stable. It has a much smaller mass than an alpha particle and a charge of either plus or minus 1. So it does not interact as strongly with matter as alpha and penetrates farther. It is also ionizing. Beta radiation does not travel as far as X-rays or gamma, discussed later. Beta radiation is emitted from both natural sources and man-made radioactive substances. Phosphorus-32, iodine-131, and potassium-40 are all examples of beta radiation emitters. Another form of ionizing radiation, neutron radiation, happens when neutrons are ejected from an unstable nucleus as it attempts to become stable. Because neutrons are neutral, they ionize by bumping into electrons or nuclei to knock electrons out of orbit. Neutron radiation is the only type of radiation which has the ability to make another material radioactive or to have unstable nucleus. This process is called nuclear activation. It happens when the ejected neutron joins the nucleus of another atom, giving it an imbalance of protons and neutrons compared to what it needs to be stable. Free neutrons are unstable themselves. If they do not interact with matter, they will decay into other forms of radiation. Because of its ability to deposit large amounts of energy deeply into materials, neutron radiation is considered the most dangerous and damaging form of nuclear radiation. Humans have also made equipment to make beams of charged particles. Particle accelerators use electric fields to bring charged particles up to great speed. These accelerated particles are not coming from the nucleus of an unstable atom, so they are not nuclear. They can, however, trigger nuclear interactions that produce nuclear radiation. Depending upon the design, the output can be a beam of charged particles, or the charged particles can be used to create beams of electromagnetic radiation. Electromagnetic radiation can be considered as waves or a stream of non-material particles called photons. One property of electromagnetic radiation is that it travels at a fixed speed in empty space and travels more slowly if traveling through a material. While there are several types of electromagnetic radiation, they are all basically the same, but with a different frequency or wavelength. Their energy increases as you move from low frequency long wavelength to high frequency short wavelength. Those frequencies below ultraviolet are non-ionizing, and those above are ionizing. UV light has some, but not all, frequencies which are ionizing. Electromagnetic waves are created from accelerating electric charges, which create oscillations in surrounding electric and magnetic fields. They have properties of material waves like reflection, transmission, and diffraction. How they behave when they interact with matter depends on their frequency, wavelength, or photon energy, which are interrelated. Physically identical to visible light, gamma and X-ray radiation are both in the high energy portion of the electromagnetic spectrum. Gamma and X-ray radiation are as damaging as beta radiation, although they have no mass and carry no electric charge. With no mass or charge, gamma and X-ray radiation could potentially travel forever in materials. We can reduce the number of gamma rays or X-rays by shielding with thick layers of dense materials like lead or concrete. So how are they different? Their source. Unstable atoms will emit gamma rays from their nucleus when they have too much energy. Gamma ray emission is preceded by an alpha or beta emission. Common sources are technetium-99m, cobalt-60, and iridium-192. X-rays are produced by machines by hitting a target, such as a piece of tungsten, with fast-moving electrons. It is important to remember that hitting a dense material with beta radiation or high-energy electrons can produce X-rays. This is useful when building an X-ray machine, as the outgoing X-ray radiation can be directed using a collimator so that it will escape the device in a particular direction. But if the X-rays produced are not desirable, they must be shielded for as well. With radioactive decay, it is not uncommon to have mixed field radiation or a combination of types in the same workspace, as gamma is preceded by an alpha or beta emission or created as a result of neutron irradiation. If a pure source is needed, the unwanted types need to be shielded if possible. You may have heard of cosmic radiation. It is a term to describe particulate radiation that reaches the Earth from space. It is a mix of different subatomic particles. Electromagnetic radiation also travels through space to Earth. The Earth's atmosphere protects us from a great deal of radiation that comes from space, but not all. If it did, we wouldn't be able to see anything in space, among other concerns. Energy can be also transmitted through vibrational waves in a material. We call the material that transmits the waves a medium. These types of waves need a medium to travel through, unlike electromagnetic waves, which can travel through empty space. Technically, they are radiation because energy travels out from a source in straight lines, but they are not what we think of when discussing radiation protection. Examples of waves which require a medium are sound, ultrasound, seismic waves, waves in water, etc. They are not ionizing and outside the scope of this webinar. Alpha particles are used where a stream of energetic particles which do not penetrate far are needed. Americium-241 is commonly used in smoke detectors. Polonium-210 is used as a source of positive charge to attract negatively charged particles from the air in static eliminators. Nuclear sources are beneficial because they can be used in remote areas as they do not require an external source of energy. In the case of alpha sources, plutonium has been used as a propulsion source in spacecraft and as an energy source for thermoelectric heaters in space. Strontium is used in a variety of remote locations as an energy source, remote sensing stations for monitoring the weather or earthquakes, on buoys in the ocean, and on offshore oil platforms. Beta radiation is used when there is a need to penetrate a material for short distances or as a source to induce the emission of other forms of radiation. Beta radiation is used to treat cancer, as a tracer material in medical scans, and in industry as part of devices called nuclear gauges, both of which we will discuss later. Beta sources are used when getting a PET scan. PET means positron emission tomography. If you remember, beta radiation can be in the form of electrons or positrons. In a PET scan, the subject is injected with biologically important compounds such as sugar, water, or ammonia molecules, tagged with a radioisotope like carbon-11, nitrogen-13, oxygen-15, or fluoride-18. Other examples of tags are gallium-68, zirconium-89, or rubidium-82. As different parts of the body use these tagged molecules, they concentrate in certain organs and tissues. The positron emissions are picked up by an external scanner. Neutron radiation is extremely dangerous, highly regulated, and not found in most workplaces. When it is used, it is often for research or analysis purposes, such as exploring the composition of materials, crystalline structures, thin films, engineering analysis of strain, and imaging and 3D imaging of materials. It is also used in the medical production of isotopes, nuclear energy production, and nuclear gauges. Nuclear power production currently uses the breaking apart of nuclei, called nuclear fission, to heat water. The hot water generates steam to drive turbines which produce electricity. This is a very efficient process, and nuclear reactions produce much more energy per kilogram of fuel used than the chemical reactions which happen during the burning of fossil fuels. So the amount of waste produced is small. But the waste is radioactive and remains that way for years, so it must be safely stored during this time. Canada has been a leader in the global nuclear sector. One contribution is the development of the CANDU reactor. CANDU means Canadian Deuterium Uranium. Features include its use of natural uranium and the use of heavy water to cool the fuel and moderate the neutrons. CANDU reactors have excellent uptime and safety records. There are currently 19 operating CANDU reactors in Canada, 18 in Ontario, and 1 in New Brunswick. There are 10 CANDU reactors currently operating elsewhere in the world. In a CANDU reactor, thermal or slow-moving neutrons are used to split apart uranium-235 by turning it into more unstable uranium-236. It breaks into two pieces called fission fragments. In this process, energy is released as gamma photons, the kinetic energy of the neutrons, and the vibrational energy of the fission fragments. 2 to 4 free neutrons are produced, which can go on to interact with other uranium-235 atoms, continuing the reaction. Some of the energy released is converted into heat, which creates steam to run the turbines. Particle accelerators use electric circuits and resulting magnetic fields to bring charged particles to great speeds. They are used in research of the fundamental properties of matter. By colliding subatomic particles, scientists can find new structures of matter. They are also used in other applications of research. For example, the Canadian light source in Saskatoon is a synchrotron, which produces beams of photons. Although it produces photons, a major component of its design is a linear particle accelerator. Scientists use it to do experiments in the areas of physics, chemistry, biology, animal and human health, agriculture, engineering, archaeology, geology, and paleontology. Proton-heavy nuclear isotopes for medical uses can be made using particle accelerators that produce beams of photons. Linear accelerators can produce X-rays 300 times more energetic than diagnostic X-rays to treat cancers without surgery. This field is called radiation oncology. These X-rays are very high energy. Because of this, machines generating X-rays in this energy range are under federal regulations, whereas lower energy X-ray machines are under provincial jurisdiction. We will now look at uses of electromagnetic radiation. Remember, although they are all part of the electromagnetic spectrum, the different types interact differently with matter due to their differences in frequency, wavelength, or photon energy, which are interrelated. We will start with the low frequency long wavelength and go to the high frequency short wavelength. Please note that there are different sources which give slightly different ranges for frequency and wavelengths for each type, as there are no hard and fast cutoffs. The numbers shown above here are from NASA, but you will find different ranges listed elsewhere. Radio waves have the shortest frequency and longest wavelength of the electromagnetic waves. They can easily pass through the atmosphere and most building materials. Most radio waves can bounce off the ionosphere, a layer in Earth's atmosphere, so we do not need satellites to reflect them back to Earth. They can easily be reflected compared to highly energetic electromagnetic radiation. They do not transfer much energy to the materials they hit, so they are non-destructive. They are used for communications, including Wi-Fi, heating, remote controls, and used in the process of creating an MRI scan. Microwaves are typically considered the upper range of the radio frequency band. They don't reflect off the ionosphere, so satellites are needed to direct them back to Earth. They tend to get blocked more easily than the lower radio frequencies, so they require a more clear line of sight between emitter and receiver than other radio waves. Because they have a shorter wavelength, microwave antennae are smaller than other radio wave antennae. Microwaves are used in heating. They penetrate into the material and vibrate water molecules. They are also used in communication, including satellite communication and radar. You have probably heard of a laser, but did you know that it was predated by maser, the microwave version? Maser stands for microwave amplification by stimulated emission of radiation. It creates a beam of microwave radiation that all has the same frequency, phase, and direction. Masers are used in satellite and air-to-air communication, radio telescopes, and radar technology. Infrared light is just below red light in terms of photon energy and frequency. Infrared radiation is invisible, but feels warm because it tends to heat material it hits. It is used in electric heaters, cooking, remote controls, and thermal imaging cameras. These cameras detect the thermal energy radiated from objects in the form of infrared. Visible light is the portion of the electromagnetic spectrum detected by the human eye. While individual humans might have a slightly different range, it is considered to be 400 to 750 nanometers in wavelength. The colors of the rainbow are the spectrum displayed in order of increasing frequency and decreasing wavelength. Visible light can transmit through glass and is easily reflected off smooth surfaces. The applications of visible light are too numerous to list here, but very familiar. We will, however, mention laser as it is a pervasive technology that is provincially regulated. Laser stands for light amplification by stimulated emission of radiation. The traditional laser design is comprised of a chamber within which light reflects back and forth multiple times before escaping. The light that is emitted from a laser is monochromatic, meaning it all has the same frequency, coherent, meaning they're all in phase, and travels in one direction. A laser is a device which gives off light, typically in the visible range, but they can also produce infrared and ultraviolet. This is different from the maser, which produces monochromatic, coherent, unidirectional microwaves. Lasers have many uses in modern society. They are found in electronic devices, used in research, dermatology, tattoo and hair removal, in surgery, holography, in weapons and guidance systems, and in communications, amongst others. The applications of visible light are too numerous to list here, but very familiar. We will, however, mention laser as a pervasive technology that is, Ultraviolet light is just above violet in frequency. Lower energies of ultraviolet light are not ionizing, but can produce photoelectric effects. Higher frequencies are ionizing. Exposure to ultraviolet can cause cataracts and increase your risk of getting cancer. Although it has these health effects, it is still used frequently by people to tan. Whether the source is the sun or a tanning bed, the possible damage is the same. Others uses of ultraviolet light include using low energy UV to cure gel nail polish. You should ensure UV light for this purpose are low energy UVA. Fluorescent pigments and dyes absorb ultraviolet light, which is invisible, and re-release some of its energy in the visible light range. This is what makes them look so vibrant, because your eyes see the energy from both the reflected visible light and the re-emitted UV light. Fluorescent inks or embedded fibers are used in products to prevent counterfeiting. When UV light is shone on them, they glow, whereas in regular light, they do not. UV is also used to sterilize surfaces and liquids, killing bacteria and viruses. The light needed to sterilize is energetic enough to increase your risk of getting cancer, so radiation safety principles must be in place for users. Some insects can see ultraviolet as well as some mammals and birds. They can see patterns in nature which are invisible to us. Gamma rays have all the properties of X-rays, but are naturally occurring. So many of the uses are similar to X-ray, but used in areas where it makes sense to have a natural source rather than a machine that is plugged in. Medically, gamma is used in brachytherapy cancer treatment, imaging, to kill tumors with a device called a gamma knife, and in a process called sentinel node dissection. In sentinel node dissection, a radioactive tracer or a dye is injected into an area near a tumor. Imaging is used to see where it concentrates. This helps the doctor to see how lymph travels from the tumor to the lymph nodes, so they can remove a node or two to check for cancer. Technetium-99m, a gamma emitter, is commonly used. It is also used for the sterilization of food or other perishable items which might have living things deeper than the surface, like art or antiques. Gamma is used in industry for imaging, in nuclear gauges, and the cross-linking of polymers. It also has use in materials analysis, for example, spectrometry. X-ray machines have many uses outside of a medical setting. These include XRF materials analysis, analytical materials analysis, food production quality control, baggage scanning, and electronic parts inspection. In medicine, X-rays are used in human and animal health care for imaging purposes. These include dental X-rays, diagnostic X-rays, and mammography. Veterinarians use X-ray equipment for similar reasons, but have unique considerations due to their clientele, such as how to keep the patient immobilized. CT scanners are X-ray machines which take numerous X-rays to form a series of 2D or a constructed 3D image of an area of the body. Due to the length of time spent in the X-ray field, having a CT scan exposes a patient to more ionizing radiation than a single X-ray. There are some medical procedures which use more than one type of radiation. Two examples are SPECT imaging and brachytherapy. As stated before, it is common for sources to produce more than one type of radiation. If one form is not useful, it is shielded for if possible. In SPECT imaging, a combination of an X-ray in the form of a CT scan and a gamma-emitting radioactive tracer are used to create detailed 3D images. Tracers used include iodine-123, technetium-99m, xenon-133, thallium-18, and fluorine-18. Brachytherapy is the use of radioisotopes for cancer treatment. This is an example where you can use a different type of radiation to do a similar job, with the selection dependent on the specifics of the task. The source and strength used depends on the cancer being treated. Typically, beta and gamma sources are used, but sometimes alpha is as well. Cobalt-60, iridium-192, ruthenium-106, gold-168, palladium-103, iodine-125, and radium-223 are all used for these purposes. One example in industry of use of radiation which could have a different source type to perform a similar job is a nuclear gauge. Previously mentioned, nuclear gauges are devices which contain a shielded radioactive source. They will produce a beam of beta, neutron, or gamma radiation when opened. The source type selected depends on the material the gauge is used on and the task being performed. Nuclear gauges are typically used to determine the thickness or density of a material or the fill level of a tank. Fixed gauges tend to be used for monitoring. The example in the diagram is used to monitor the level of liquid in a tank. Other fixed gauges might monitor the thickness of paper or plastic products being produced. Portable gauges are used in the field. You might find portable nuclear gauges being used in construction, the mining and oil industries, or manufacturing. For example, they're used to check the compaction of soil or determine the composition of layers of earth. For more information about radiation protection in healthcare, industry, in your home, contact the CNSC, the Radiation Protection Bureau, or the Radiation Safety Institute of Canada. We can provide information specific to your provincial regulators. We hope you enjoyed this webinar. Founded in 1980, the Radiation Safety Institute of Canada is an independent, not-for-profit organization offering a variety of informational, consultation, and laboratory services focused on radiation safety. If you have any further questions about radiation at work or at home, please feel free to contact us toll-free at 1-800-263-5803 or by email at info@radiationsafety.ca. Visit us on the web at www.radiationsafety.ca or find us on Facebook.